Okay, welcome to lesson 22, titled Proportional Relationships Revisited. And in this lesson, we're going to look again at constant rate problems, and we're going to see how they can be described by a linear equation in two variables. We're also going to look and see that the slope of the graph is the constant rate in the problem. And we're going to see that those types of relationships can be represented by graphs, equations, and tables. And you can use those interchangeably to make to come to conclusions about those proportional relationships. Okay, so let's look at an example. This is example 1. You don't have these examples in your notes, so you will need some graph paper and yeah, just some graph paper, and then you can take notes on that too as we go along. But there's no need to write all of this down. You can just look at the problem. Okay, so example 1 says Erica set her stopwatch to 0 and switched it on at the beginning of her walk. She walks at a constant speed of 3 miles per hour. And so we're asked to present this information as an equation in two variables. So as an equation in two variables, a table of values, and a graph. And so before you get started on that, let's just go back and talk about what do we mean by constant rate. And so this example here has to do with speed, how fast she's walking, the distance she walks, and the time it takes her to do that. Because her rate is constant, that means that if we looked at her average speed, which would be her total, so average speed would be equal to total, well, not total, we'll just say distance traveled. Distance traveled divided by the amount of time. So if I traveled 6 miles in 2 hours, I would be going 3 miles per hour. So average speed is distance traveled over time. So if our definition of constant rate is that the average speed over any time interval in that we're talking about is equal to some constant. It's always the same. The average speed will not change. So no matter what our time interval is during her trip, her speed is always going to be 3 miles per hour. So that is a constant. Okay, so now that we get that out of the way, and we talked about that a lot back in an earlier lesson. So this is going to be an equation in two variables. So what will the two variables represent in this problem? So pause the video and think about that, and then come back and we'll talk about it, and then I'll let you get started on presenting this information as an equation, a table of values, and a graph. Okay, so in this scenario, we have some different quantities we're going to talk about. We have distance, and our distance is going to be miles. Okay, and we've got time, and that's going to be measured in hours in this case. Some of you thought maybe one of our variables could also be her speed, okay, which is miles per hour, okay? But notice that the speed is a kind of a combination of the other two variables. So our two variables are going to be distance and time. So I don't know if you came up with that or not, but going to be distance and time. And in all of these problems that you're going to be doing in this lesson, time is always going to be a variable. It might not always be distance, but time will always be a variable in these rates. So it might be the number of pages typed, or the amount of lawn that got mowed, or the amount of wall that got painted, pages read. There's different things you might be measuring, but we're always going to measure it against some unit of time. So time is generally going to be the x variable on the horizontal axis. Because we think about the variable on the horizontal axis, we call our independent variable. So that's kind of the thing that you get to manipulate. And then we're going to use y for the other, that would be the dependent variable. So we think of time as an independent variable because we can say, okay, I'm going to travel for 3 hours or whatever. And then the distance depends on the amount of time. So the distance is the dependent variable. It's somewhat of a convention. In other words, there's not any real reason why we do it that way, but we generally have time being on the horizontal axis whenever time is one of the variables. So just remember that as a rule of thumb. Okay, so you're ready now. So we know that we're going to use y to be the number of miles, and x is going to be the number of hours that she walks. And right here, miles and hours. And then you're going to write an equation. Now remember, you know that her distance over her time, right here, her average speed is always a constant. And we know what that constant is. So that should give you a big hint in writing this equation. And okay, so go ahead and work on that with a piece of graph paper. Remember, you're doing an equation in two variables, and it's a very simple one. A table of values for her walk, and you can choose reasonable length of time for this walk, and then also a graph. Okay, so go ahead and work on that. Okay, so hopefully you've worked on this, but your table might look something like this. She could have different numbers in it, but if she walks for 0 hours, she's going to go 0 miles. If she walks for 1 hour, 3 miles, 2 hours, 6 miles, 3 hours, 9 miles. So there is that situation of Erica's walk represented by a table. Okay, we can also represent this by an equation. So I'm going to do that down below here, and then we'll do the graph. So the equation, I know that her distance divided by her time is equal to a constant rate of 3. So that means that I can say, since distance is y and time is x, I know that y over x is equal to 3, or I could even call it 3 over 1 if I want. So the equation then could be found by cross multiplying here and here, and I would get y times 1 is equal to 3 times x. So there's my equation. I could also look at the table and come up with an equation straight from the table, just looking at the relationships there. Okay, and then I can also represent this with a graph. Go ahead and put a couple of my points on. And then I can connect the line. I guess I could do a real line with that. Okay, so there's that situation represented with a line, a table, and a graph. So let's look at this. And so the slope of this line we know is 3 from the equation and from the graph. And actually we could see it from looking at two data points, any two data points on this graph. We can see what the slope is. So we would have a slope triangle here, and then we could look at another one here, and even here is another point. And remember, we know that these are all similar triangles, and so they're all going to result in equal ratios in the same slope calculation. So this line has a slope of 3 the entire way. And so what we can see here is that the slope is, like we saw before, is equal to the rate of change. And it's the rate of change of her position with regards to time. So she's moving 3 miles every hour. And so that's what we see on this graph. Every hour she goes another 3 miles. Okay, so it's pretty cool. It's very useful. A lot of times people don't want to write an equation because they say they can just solve the problem, but a lot of times we don't necessarily have a question we're answering. We just want to represent something with an equation, and it might be because we're writing a computer program or we're trying to communicate it to somebody else. So being able to actually write these equations is pretty important as you go on in math and science. So, okay, let's look at another example. Okay, example 2. Again, you don't have this in your notes. A faucet leaks at a constant rate of 7 gallons per hour. We're told that Y gallons leaks in X hours, starting from 6 a.m. when the leak began. Express this situation with a linear equation in 2 variables. So once again, we have a constant rate problem. So let's see. So we know that the ratio of gallons to hours is going to be a constant for the whole time. So see if you can so think about that, and then quickly come back and we'll do this one together. Okay, so our linear equation is going to look something like this. We know Y gallons in X hours is equal to a constant, and we're told that that constant is 7. 7 gallons every hour, which could be even written like this: 7 gallons in each 1 hour period. And so our equation can be found by cross multiplying here. And the equation is y times 1, or just y, is equal to 7 times x. So that's the linear equation in 2 variables for this situation. Now we're given a table, and it says another faucet leaks at a constant rate represented by the table shown. Determine the rate that this faucet leaks. Which faucet has a worse leak? Okay, so there's a couple ways you could figure out the rate that this faucet's leaking. And one would be just to look at y over x, or gallons per hour. And so one of those could be 13 over 2, which is 6.5. Okay, so this faucet is leaking at a rate of 6.5 gallons per hour, and our other faucet is 7 gallons per hour. So Obviously, if we want to know which faucet has a worse leak, the one that's leaking faster is the one that we would call a worse leak. So this first faucet has a worse leak at 7 gallons per hour. There's another way that we could find the rate of change in this equation, and this would be to find the slope between these 2 points. There'd be, we could think of this as x1, y1, and x2, y2. And we could say the difference in the y's, which would be 26 minus 13, divided by the difference in the x's, which would be 4 minus 2. And so if we simplify that, we'd get 13 over 2, which again is 6.5. So again, this is going to be the slope in this equation, right? So this equation would be y is equal to 6.5 times x. Okay, so we've got equations and tables here. We could also represent this with a graph. Okay, but we're going to look at another example. So this is example 3. In this example, it says the graph below represents the constant rate at which train A travels, and then we're asked to find the constant rate of travel for train A. So you probably need some help reading these numbers here. So this is time in hours on the x-axis. So it's 1, 2, 3, 4, 5, 6 hours. And then on the y-axis we have distance in miles, and every space is 20. So this is 20, 40, 60, 100, and so forth. So it's time in miles. So if we look at what the rate of change on this graph is going to be the constant rate. So that might not be immediately obvious. So let's think about this for a minute. So this train in 1 hour travels 60 miles. In 2 hours travels 120 miles. And so we can calculate the speed that way at 60 miles in 1 hour, or 120 miles in 2 hours, and see that the slope for this graph is 60 miles per hour. So m is equal to 60 miles per hour. So let's look at why that's the case. Let me get a different color. If we look at a slope triangle right here, so our vertical change is 120 for a horizontal change of 2. So it's the same as slope is what we're looking at. So the constant rate of travel for this train is 60 miles per hour. Okay, so the second part of this problem says train B travels 95 miles every 1.5 hours. Okay, so we want to compare train B to train A. So remember, train A's rate is 60 miles per hour. And we want to know which train is faster. So train B, if we wanted to write an equation for train B, we could say that the distance over the time, and we'll call it a decimal, the distance over the time is equal to y over x. Remember, y is distance, x is time. So we're just setting up, these ratios are equal. So this is the constant rate at one point of the trip, and then this represents the constant rate as well. So we've got, if I think in terms of multiplying both sides of this equation by x, then I end up with, and I'm going to flip it around, that y is equal to 95 divided by 1.5 times x, because this cancels out there. So we just need to do that calculation, 95 divided by 1.5, and you could use a calculator for this one, that would be fine. And you end up with y is equal to 63.3 repeating times x. So this we recognize as, this number here, we recognize as the slope in this equation, and so it's also the speed. So train B's rate is 63 1/3 miles per hour for train B. And some of you might have logically reasoned through that if you look at train A's rate of 60 miles per hour and thought about how far would train A go in an hour and a half, you might notice that train A could only go 90 miles, 60 plus another 30 in an hour and a half, and so train B must be traveling faster if it went 95 miles in an hour and a half. So, but we found train B's rate, and it is faster than train A's. So, and we did that. We had the graph for train A, and we only had the data for train B, but we could figure out the speed. Okay, this next example is a constant rate problem, and it's representing the area that Christina can paint. This graph represents the area that Christina can paint in a given amount of time. So on the x-axis is time, since that's what we usually do, and it's time in minutes. So and then on the y-axis, we have the area painted in square feet, and this is going up by twos, 2, 4, 6, 8, 10, 12, 14, 16, 18, up to 20. We're also told that her sister Tracy paints at an average rate of 45 square feet in 12 minutes. Assuming Tracy paints at a constant rate, determine which sister paints faster. So if we look at the graph, we can find out Christina's rate of painting, and I'm just going to come over here. There's good points all along here. Remember, we look for these good points to find the slope of this. Because remember, the slope of this graph is going to be her rate in square feet per minute. Square feet per minute. So we go 1 and then up to the line here, and notice that in 1 minute she can paint 4 square feet. So in 1 minute she can paint 4 square feet. In 2 minutes she can paint 8 square feet, and over here you can see in 5 minutes she can paint 20 square feet. So the slope of this line and her rate is 4 square feet. I'm going to write feet squared. Square feet per minute. So 4 square feet per minute. So we want to compare that to her sister Tracy, who paints an average of 45 square feet in 12 minutes. So assuming Tracy paints at a constant rate, determine which sister paints faster. So 45 square feet in 12 minutes is equal to, we're saying that's equal to a constant. And so that's going to be our y square feet in x minutes. So our equation is y is equal to 45 over 12 times x. And when we simplify 45 over 12, you get, get 3.75. So her sister is painting at a rate of 3.75 square feet every minute. So her sister is slower. So we can compare that way. Okay, so let's go ahead and have you work on the exercises 1 through 5 and coming back and checking against the video as you do them or as you need a little bit of guidance. Okay, so go ahead and work on those on your own, and I encourage you, don't just gloss over writing the equation. Write the equation. These are all going to be in the form of y equals some number times x. So, so go ahead and write those, and remember, we always want time to be on the horizontal axis, so that's going to be your x variable. So, okay, go ahead and work on those exercises and then come back and check them. Okay, so if Peter can paint a wall at a constant rate of 2 square feet per minute, and we're assuming he paints an area y, so y stands for the area in square feet, after x minutes, express this situation as a linear equation in 2 variables. So we know that our constant rate is going to be the square feet y over the time x, and that's going to be equal to 2 square feet per minute. Okay, so I've left the units off, but we know what they are. 2 square feet per minute. And so I can find this equation by cross multiplying or simplifying, and I see that it's y is equal to 2 times x. And once again, notice our rate is the slope of that equation. So we can sketch the graph of the linear equation in 1 minute. In 1 minute, we will have painted 2 square feet. In 2 minutes, 4. And in 3 minutes, 6. Okay, so notice we got to pay attention to the scale here. So these grid lines are each worth 2, and these are each worth 1 minute. Okay, so we can now draw our line right through those points. And then we're asked to, actually I want to make that longer. So we sketch the graph. Now using the graph, part C, using the graph of the equation, using the graph or the equation, sorry, determine the total area he paints after 8 minutes, 1.5 hours, and 2 hours. So and then you're given a clue here. Note that the units are in minutes and hours. Okay, so we've got time in minutes here. So in 8 minutes, we can use the graph and come up here and read that he would paint 16 square feet. So in 8 minutes, that would be 16 square feet. In 1.5 hours, I can use the equation y equals 2x, except that x is time in minutes. So in 1.5 hours is 90 minutes. So y would equal 2 times 90, or 180 square feet. 180 square feet. And then in 2 hours, which is 120 minutes, it would be 240 square feet that would get painted. So I'd be using the equation for that, but I could use the graph for the other. All right, let's look at exercise 2. And again, pause this if you haven't done it yet. The figure below represents Nathan's constant rate of walking. And so we can look at it and read distance in miles on the vertical axis and time in hours here. Then the question says, Nicole just finished a 5-mile walkathon. It took her 1.4 hours. Assume she walks at a constant rate. Let y represent the distance Nicole walks in x hours. Describe Nicole's walking as at a constant rate as a linear equation in 2 variables. Okay, so for Nicole, we've got her distance y over her time x is a constant rate, and we have one, we know that she can go 5 miles in 1.4 hours. So that gives us our equation. In this case, I just want to get x on the other side. So I'm going to multiply both sides by x. Allows me to cancel it out there and rewrite this equation as y is equal to 5 over 1.4 times x. And that's her rate. And so we want to simplify that by doing the division. So we have y equals, and when I do this division, I get about 3.6 times x. So what that's telling us is that the rate for Nicole is about 3.6 miles in 1 hour. She went 5 miles in 1.4 hours. She goes about 3.6. If I wanted it exact, which in a linear equation I generally don't want to use an approximation, I could just write this as a nice fraction. So we could write it as, let's get rid of this. So it's about 3.6, remember that. But we could write it as 5 over 1.4. If I multiply by 10, I would get 50 over 14, just to make 1.4 a whole number. And then I can see that I could reduce that to 25 over 7. So a more exact way to write this equation would be y equals 25 sevenths times x, and her rate is 25 sevenths miles per hour. So part B of this asks you to determine who's faster. Well, so we need to find the rate off of Nathan's rate off of the graph, and he in 1 hour goes 4 miles and 2 hours goes 8. So Nathan's rate, his slope here, and his graph is y equals 4 miles per hour times x. So we can see that 4 is greater than 25 sevenths, because it would be 28 sevenths. And if we did the division, we saw it was about 3.6. So Nathan is faster. Okay, let's move on. Exercise 3 is typing. So here we're talking about pages of text in a given amount of time. So our rate is going to be how many pages per minute that different people can type. So Susan can type 4 pages of text in 10 minutes. Assuming she types at a constant rate, write the linear equation that represents the situation. So again, we're going to let x be the time in minutes. And so we'll let y be the number of pages. Whoops. Y is the number of pages. So we know this is constant, pages per minute. And we know that Susan can do 4 pages in 10 minutes. So that gives us our equation, but we want to write it in sort of our standard y equals mx form. So we've got y is equal to 4 over 10 times x. And I can simplify that to 2/5 if I want to, and I do. So 2/5 x. Okay, so now we have a table that shows the number of pages that Anne can type, and Anne also is typing at a constant rate. So Anne can type 2 pages in 3 minutes, 10/3 of a page in 5 minutes. So we'll go with this first one. So who types faster is our question. We could do this one as an equation as well, because pages typed over minutes is going to be 2 to 3. So this equation here is going to be y equals 2/3 times x, compared to the first one, which is y equals 2/5 times x. So that the faster typer is going to have a greater rate, and so I want to compare 2/5 with 2/3, and I know that 2/5 is less than 2/3, and so Susan is a slower typer, Anne is the faster typer. And even just talking about the rate will help you see that, because if it takes Anne 5 minutes to type 2 pages, that's obviously slower than, or not Anne, this is Susan. 5 minutes to type 2 pages is slower than 3 minutes to type 2 pages. So it takes her a longer amount of time to do the same amount of typing. So, but we can also see it by comparing those, the slope of the graph or the rate. Okay, so now we're going to talk about birdhouses. Phil can build 3 birdhouses in 5 days. Assuming he builds birdhouses at a constant rate, write the linear equation that represents the situation. Okay, so we're going to again let our x variable be the time, and that's going to be days. And we'll let our y variable be the measure of whatever it is that's happening. So we can let y be number of birdhouses. Abbreviating here. So the number of birdhouses per unit of time or per day is going to be, our example here, our constant rate is he can do 3 birdhouses. That's goes with our y, number of birdhouses, in 5 days. So our equation here, our linear equation that represents this situation, would be y equals 3/5 times x. So remember, I can take and think of multiplying both sides here by x. So that gives me this linear equation that represents how fast Phil can build birdhouses. So what this is really saying, when you think about it, it's saying he can build 3/5 of a birdhouse in 1 day. So if he worked for 1 day, if x was 1 day, he would build 3/5 of a birdhouse. Okay, so then you're also given this graph here, and this figure represents Carl's constant rate of building the same kind of birdhouses. Who builds birdhouses faster? So let's look at this graph. So we're going to find a good point here to find the slope, and this is the first one this is the first one I see right here. So on this graph, in 4 days, Carl can build 3 birdhouses. So Carl's slope, let's see what this is. This is 3 birdhouses in 4 days. So this equation is y equals mx, right? So this is y equals 3/4 x. Okay, so Carl can build 3/4 of a birdhouse in 1 day. That's his rate. And so we need to compare that to the other guy, whatever his name was. So remember, his rate was 3/5. So the one we had before was y equals 3/5 times x. So who's the faster birdhouse builder? Well, we have to compare the slope, and so we've got 3/4 and 3/5. 3/4 is greater than 3/5. It only takes Carl 4 days to build 3 birdhouses, and it takes what was the other guy's name? Phil. 5 days to build 3 birdhouses. So obviously Phil is slower. Carl is faster. Carl wins. Okay, so explain your general strategy for comparing proportional relationships. So on this one, you should have said something to the effect of that you're looking specifically at the rate of change in each situation. So in this one, the rate of change 3/4 and 3/5. We're looking at that and comparing that. So the greater rate of change will be the faster birdhouse builder, faster painter, faster walker, whatever it is. It's changing more with respect to time. So that's going to be how we compare. So it's kind of something to that effect should be your general strategy. Okay, so let's just summarize what we looked at here. We got experience with writing linear equations in 2 variables to represent constant rate problems. I think these are all fairly simple situations that are pretty easy to understand, but still sometimes we're not quite sure which variable is standing for what and how that should be represented. So, so it's good to have some practice at that. So the problem set and the exit ticket will give you even more practice. And then the second thing, when given information about two proportional relationships, we can determine which is less or greater by comparing their slopes. So we can tell things about speed by looking at the slopes of these graphs, because the slope of the graph is going to be the rate of change. Okay, so go ahead and get going on the exit ticket and problem set. And we'll see you back here for lesson 23.